Gauss-Seidel method. Right? So there are 3 more classes. Today we will complete Newton-Raphson method. Next week we will have 2 classes. So then we will complete this. How to apply Newton-Raphson method for power solution. And fast decoupled method, which is actually a derivation of Newton-Raphson method. So basically in these 3 classes we are discussing Newton-Raphson method, which is most widely used for power solutions. And you have been given some problems on, can you simplify problems on Newton-Raphson method in your lab. Okay. Load flow experiments. Okay. So we'll start with today's topic is only to understand the Newton-Raphson method. So many of you do not have a background on numerical methods. Okay. Newton-Raphson method is part of a set of methods known as numerical methods. See, there are 3 kinds of solutions to any problem. One is analytical method. Analytical method. Okay. One is analytical method. What do we mean by analytical method? Analytical method means you solve an equation. For example, solving a simultaneous equation. So you have some equation or that quadratic equation formula minus b root over b square minus 4. So you have only one solution. You solve it. One solution means you have multiple variable values, but solution is only one. There is only one set of solutions that you will get. Okay. Whereas in numerical methods also you will find the same solutions, but here there is a small difference. If you start from a very different location, you might get to a infeasible solution. That is numerical method. The third type of method, that is based on, as you have heard, based on soft computing. What is soft computing? What is soft computing? Have you heard the word soft computing? What is the meaning of soft computing? Anyone? What is soft computing?
Computation based on artificial intelligence and machine learning.
She said computation based on AI and machine learning. So this kind of soft computing started with some kind of algorithms, okay, which are now AI and machine learning. Okay, but earlier days the first, you can say the holy grail is genetic algorithms. So what we do in soft computing, we don't use any equations. In first case, analytical method, you have an equation, you solve it. In numerical method, the same equation is solved in iterative manner. Okay, but still there is an equation. In soft computing, you just give a set of solutions. You go on checking every solution, and then you find your solution, that is your final solution. Okay, but what is the problem with soft computing? You need lots of computational power, because you need to search the whole solution space. Analytical method directly point you, okay, here is where the solution is. In India, you go to this location, and at this location you will find your objective. That's analytical method. Numerical method, okay, you start from this place, then go another 1 kilometer, another 1 kilometer, within 5 kilometers you will find the solution. Soft computing, go everywhere throughout the India, wherever you find it feasible, that is your solution. But for that you need lots of cost. You need to travel cost, time, everything is required. Okay, and if you have high computational power, equivalent, if you have lots of, you have a deep pocket, you can use flights, you can go everywhere and find your solution. So that is soft computing. Okay, so why it is soft? Because it is not using any mathematical equations or analytical solution like derivatives, all those things it is not using. Okay, so here now we are seeing the numerical methods. Okay, Gauss-Seidel is also one numerical method. Numerical methods are inherently iterative. We start with the initial guess, then we further refine it. Okay. Okay. So we will go to the basics of numerical methods. So before that, these 2 questions, question number 1 and 2 are based on Gauss-Seidel method. For the solution I have given to you. In exam also similar questions will be asked. Question number 3, 4 and 5 are based on Newton-Raphson and fast decoupled. Question number 3 and 4 are the type of questions that you might see in your GATE exam. Okay, 3 and 4. I have taken it from NPTEL course, but these are the type of the questions that we will discuss when we discuss NR method applied to power flow problem. Today we will discuss only the core, the crux of the NR method. Okay. So no problems today except one example. Okay. Newton-Raphson method. So what is the principle of Newton-Raphson method? So as you can see from the very first slide, it is based on derivatives. It is based on derivatives. But it is before the arrival of soft computing or AI ML based algorithms. NR method was the most common. And today also, all the established algorithms which are used for power flow are NR methods. Normal genuine computing power within limit it requires, so it doesn't need too much computational power. Most of the power flow algorithm that is used by this power sector utilities use NR methods. Okay. It is a successive approximation procedure based on the initial estimate of the unknown. So you have got two things. One is an initial estimate that you will give. So if you want to give a bus voltage initial estimate, how much you will give? How much? 2. How much? See, power flow problem means solving the bus voltage magnitude and angles. So what should the initial estimate that you should give? And remember that it is always in per units. 1, 0. So the general initial estimate is known as 1 per unit magnitude, 0 degree angle. It is also known as Dirac star. Or bus voltages you start with this one. Okay. Now again, we are now trying to find the solution of the equation fx is equal to c. So first thing you write in your copy, the equation is fx is equal to c. Okay, that is our equation. Our equation will be in that form. Okay. Then we get x0, which is an initial. Okay. Step 1 is the equation. In our case, the power flow problem. Step 2 is the initial case. Step 2 is the initial case. Okay. Right. Remember that x0 is the initial case, it is not a solution. So there must be some delta. Okay, for example, it is 1, but actual value is result is 1.05. So there must be some delta which will make this equation solved. Okay. So therefore fx0 plus delta x0 must be equal to c, and this x0 plus delta x0 is an approximation of the result for x. Okay. So this is the solution that we want to achieve. Our objective is to find this delta x. Okay. Now this is what you need to understand, and this part is only the derivation. Nobody will ask you the derivation. So what we do? We do a mathematical expansion known as the Taylor series. See, remember that this is not applicable to soft computing based methods. We don't bother about any kind of derivation or derivative because we have lots of computing power. We'll just go around and find a solution. Okay. Okay. So when we expand it, the expansion is like this: fx0 df by dx is 0, 1 by 2 factorial, and so on. Okay. And we neglect this because this delta x is a very small quantity, 0.05, 0.005. When it is squared, it becomes further smaller. So we will take only the first part. That is the theory of. So we take only this. This is the theory of. So write down. Expanding in Taylor series and neglecting higher order terms. Expanding in Taylor series and neglecting higher order terms. Expanding in Taylor series and neglecting higher order terms, we get fx0 plus df by dx0 delta x0 is equal to c, because we neglect this term. We neglect the higher order terms, and therefore we get fx0 df by dx0 delta x0 is equal to c. Okay. Therefore, from here we see that this term can be be considered to be the small increment. Okay, so we will denote this term as delta C0. Okay, we will denote this term as delta C0. Okay, which is df by dx 0, delta x 0. So this term is delta C0. Remember it. Okay. So how our equation will look like now? So this is step 4. We denote delta C0 as this term. Okay, only this part, and therefore we get delta C0 equal to C minus f of x0. Okay, so what it means? The increment is equal to the initial function value minus that you will get by your initial case. So this is the difference. Okay, that is your change in the first iteration. So we go on iterating till this becomes minimum delta C. Okay, next. Now coming to the formula. Okay, so that is the derivation stage. Okay, now working formula. You write working formula. So what is the which one?
So delta C.
This is the Taylor series expansion. This is Taylor series expansion equal to C. Okay, but we know that x0 is our initial guess. Okay, so C minus fx0. C minus fx0 is this term only because we neglect this term. So this term is known as, we will denote as delta C. Okay, but what is exactly this? This is the difference between the actual function value minus the function value that we will get because of our initial guess. For example, f2 is 0. Okay, but if we take f1, we get 3. So 0 minus 3. So minus 3 is the difference. Or with respect to load flow, suppose the initial power demand was 400 megawatt. Okay, but our initial guess makes the power demand to be 390 megawatt. So 10 megawatt is delta C. Okay, so next is the working formula. So the working formula for Newton-Raphson method is given by, so from the previous slide we will get this formula for x1. So what you see, x1 is equal to x0 plus delta C0 by this, or in general this is the formula. Okay, so that means what is our objective? Our objective was to make an initial guess, then find out the increment that we will make to reach our final solution. Now what is the increment? That increment we will get by dividing the initial difference due to our initial guess. For example, f3. Suppose f3 was 20 and f1 was f5 was 0. Okay, f3 was 20, f5 was 0. Now f5 is the solution. We have started with 3. Okay, so how to find out this difference? 3, 5 minus 3, 2. How to find the difference? By evaluating the function. Okay, at those two values and getting the difference delta C. So this is the function difference divided by the derivative. You see, divided by the derivative. This comes from the Taylor series. So what Newton-Raphson method wants is a derivative. What is f in our case? In our actual problem, what is f? What is our problem here? What we are trying to solve? Power flow equations. We are trying to solve the power flow equations. So what is f then? Complex algebraic load flow equations. So we have to find the derivative of load flow equations. Okay, so it must be difficult. So therefore it can be done programmatically only. Manually it is possible only for small systems. Gauss method did not require any kind of derivatives. Okay. So this is also known as Hessians. Gaussians, Hessians, Jacobian. Okay, so all those things. Okay, it's not exactly Hessian, but similar to that. You will find this term when you use the math course also. So anyway, our objective is using this equation only. Did you write these equations? So we will use this to solve a problem. So you have. Okay. Now, you see here, delta CK is a very important thing from gate also. Delta CK is equal to df by dx k into delta xk. Now this df by dx is known as jk. So as I told you, these are also known as in general Hessians, but in this particular case, these are known as Jacobians. So this is known as the Jacobian. Okay, clear? So this is for one dimensional case only. Example. So now you solve it. So our equation is fx is equal to 0. So c in this case is 0. Okay. So we have to use Newton-Raphson method to solve this. So for finding Newton-Raphson, using Newton-Raphson method, what is our working formula? So working formula is what? Delta x, what? T, iteration, or x, what was that? Delta x, k. Delta x k is equal to delta c k divided by is it? So that means we have to find out df by dx. So what is the df by dx in this case? 3x square minus 12x plus 9. Okay. Now initial guess. So we are starting with an initial guess of 6. We can start with any guess, but for this example, we are starting with initial guess of 6. So at 6, what is the value of the derivative? Find out. Find out. What is the value of the derivative at 6? Calculate.
एग्जाम में तो इनिशियल एस्टिमेट का देते हैं
Yes. Oh yes.
इधर हमारा
Always. Okay. df by dx 0 is equal to 45 of 6. It has to be calculate. 3 into 6 square minus 0 into 6 plus 9. Is it 45? So derivative is 45. So that means our delta x is equal to delta c. What is the difference? C minus fx0, c is 0. C is 0. So as you asked, c is 0 here. What is fx0? F of 6. What is f of 6? 6 cube minus 6 into 6 square plus 9 into 6 minus 4. Calculate. Is it 950? Check it. Cross check. Cross check. F of 6, is it 950? F of 6. Yes, it is 50. F of 6, is it 50? Okay. So delta C becomes minus 50. So our initial increment becomes minus 1.1. So we started with 6. So after, that means x1, x0 was 6. So x1 becomes 6 plus minus 1.11. So I think 4.9, right? 4.99 or something. Okay. Then again we will start with 4.9 and further we will continue in different iterations. Okay. So at the end of the first iteration it is 4.8889. Subsequent iterations will yield these values. Okay. Now because of this derivative, the Newton-Raphson method converges more, or it converges fast. Okay. And as you asked that day, what if we choose another guess? The method may converge to a root different from the expected one, or diverge if the starting value is not close enough to the root. Because it's a cubic one, so we have 3 solutions. Okay. But one will be of our interest, 2 will be infeasible. But that depends on, you will reach the solution depending on where you start. Okay. Okay, so this is the convergence characteristics. Okay, not required, only for reference. So that was only one dimensional case. Okay, but load flow equations are n dimensional because there are n buses, 2 buses, 2 dimensional, 3 buses, 3 dimensional. Right. So how to solve that? So in that case, so you write n dimensional case, right? N dimensional case. So first you write these equations. So these are n equations in n variables. Okay. Write down the equations. N equations in n variables. Okay, so now this is only a derivative, don't write the other part. So we expand everyone to in Taylor series, okay, and we neglect this higher order terms. We neglect it. Okay. No. Here the higher order terms are neglected, already neglected. So expanding the left hand side of the equations in Taylor series are about the initial estimates and neglecting the higher order terms. So we will get, see, every equation there are all the variables. See here, this is a kind of matrix. F1 by x1, f2 by x1, fn by x1, f1 by x2, f1 by xn, and so on. Okay. Don't write this. Okay. Now write this. Expanding the Taylor series and neglecting higher order terms, we get, write this equation. Expanding the Taylor series and neglecting the higher order terms, we get this. You won't get any question to solve problems in Newton-Raphson method. Remember that. Only the questions that will be asked is given in your at the end of the problem set. Okay. Theoretical question like give a flow chart of the Newton-Raphson method for power flow solution. Okay. Nobody will ask you the problem because that requires too much time. Or if they ask, only one iteration will be asked, and that too for 8 1. If that is asked, only one iteration. Very difficult. I'll show you how I am doing. Okay. Now this is the equation for the n-dimensional case, and this is, as you know, this is known as the Jacobian. All of you should write this because you solve the problem based on this. All of you write this. Next example is based on this. You need this equation to solve. And this in short form can be written as delta Ck Jk into Xk, or delta Xk is equal to Jacobian inverse into delta C. That means in our case, when we solve the power flow equation, we have to form the Jacobian and take a inverse of that. That's why Newton-Raphson method is computationally very demanding, because we take metric inversion. Suppose it's a 100 bus system, then 100 cross 100 matrix inversion. Okay, and you have got the mat power software. It's an open source code, so you can go through the source of the code and see how these inversions are taking place. They use some method known as sparse matrix computations, okay, to make it faster. Okay, and finally you take the increment up to get the final value. So all of you, when you write this, will solve the problems based on this. This is known as the Jacobian. And in gate exam, mostly it is repeated. There is a power system having 100 cross 100 buses. So what is the size of the Jacobian matrix? This many PV buses, this many PQ buses. What is the size of the Jacobian? It's a popular question in the gate exam, repeating question. So we'll discuss something about the Jacobian matrix. So the matrix Jk is called the Jacobian matrix, and only the zeroth iteration matrix is shown here. Right? We have to compute this matrix in every iteration. Suppose 5 iterations, 5 times the Jacobian must be computed, and including its inverse. Okay? The program in your lab, you can see all these are evaluated. Okay? Elements of this matrix are partial derivatives. These are partial derivatives evaluated by xk. We assume that jk has inverse given to. Suppose jk is computed so that it doesn't have any inverse. Okay, we map in Math 1, you must have studied about matrices. Okay, so there are some conditions whether a matrix has inverse or not. Okay, it is assumed that every step there is an inverse. Okay. Newton's method is applied to a set of nonlinear equations, reduces the problem to solving a set of linear equations in order to determine the values to improve the accuracy of the estimate. So this actually is converting into linear equations after derivative. Okay, obtaining the derivative. Obtaining the solution by direct inversion is very inefficient. A direct solution is obtained by optimally ordered triangular factorization. So there are many mathematicians, those who do MTech in power systems or electrical engineering, they will study about all various methods which can be used for theory of methods, because many of these are already implemented in software. So you can read the theory. Okay. One such method is triangular factorization. Done. Okay, now it is your job to compute. Okay, first question. You need to compute only the Jacobian for this problem. What will be the size of the Jacobian? 2 by 2. What will be the first element? Delta f1 by, just tell me the formula. Delta x1. Del f1 by del x2. Is it? Or del f2 by x1? F2. F2 by x1. And this is del f1 by x1. Okay. Okay. Del f1 by del x1. Then del x1. So what is f1 here? F1 is this. With x1 square plus x2 square minus 4 is f1. E to the power x1 plus x2 minus 1 is f2. So compute. Compute the Jacobian. First element में कौन होगा? 2x1 plus 2x2 ना? Is it 2x1 plus 2x2? First one. Yes. No, 2x1 only. Yes, only 2x1. It's partial derivative. 2x1. So the first element will be What is the second element? 2x2. Third element? E power x1. Next. Fourth element? 1. So based on the initial guess, you can find the numerical value of Jacobian. Okay. So 0.5 minus 1. So find out with the initial estimate of 0.5 minus 1. What is the value of the Jacobian for the first case? How much? 2x1 is 0.5. Okay. 1. Then
minus 2.
Initial case is 0.5 minus 1. Okay. So what is the value of the Jacobian? Tell me. First is 1. 1 is, I think this is 1.
Yes, sir.
Next is 1. This is e to the x1. Mane? 0.5. And this one?
Minus 2.
Okay, write down. 1 e to the power 0.5 minus 2 1. Let me see. Okay. 1 e to the power 0.5 minus 2 1. E to the power 0.5 माने रूट स्क्वायर रूट ऑफ 2.73 है. E is 2.73 है. Square root of 2.73 is how much? Square root of 2.73.
Sir, 3 to 1.7 that is
Around 1.6. So this is fine. Okay. So now understood how Jacobian is calculated. Now compute the Jacobian for the second one. Okay. There are 3 variables here. Okay. Now see, nowadays, suppose you want to write I have written here, this you will do later, first listen. Write a computer program, MATLAB, Octave, Scilab, Python, etc. to implement LR method. Okay. So nowadays you need not write the program, you know that. Now generative AI is there. You can give this question and tell them, give me a program in MATLAB, but you need to ask the right questions. Okay. Then it will give you the complete program of Newton-Raphson. So at least do that and run in Octave or MATLAB. If you have MATLAB, fine. If not, Octave is also very powerful. Okay. Simple. These two questions you solve by getting the code from the generative AI. So there is one course running in Swayam from ISC Bangalore. The name is Programming with Generative AI. It's a very nice course. It will teach you how to ask the right questions to get the appropriate program for your problem. Nowadays, PhD students, they are simply asking the questions to generative AI. It's giving some kind of program, they are just modifying it. So do it. Get the code from the AI and run it. Now your job is to compute this. Solve this. Find out the Jacobian and its numerical value at this initial value. Okay, do it now.